Okay, sliding over to page 2 here of our review. For the final exam, we have a problem where we're asked to determine the empirical formula for ibuprofen, and we're given mass percents of the component elements, carbon, oxygen, and hydrogen. So what we want to do here is take the mass information and turn it into moles. So I'm just going to take those percentages and change them into mass. So 75.69 grams of carbon would be how much carbon would be in a 100-gram sample, 15.51 grams of oxygen, and 8.80 grams of hydrogen. And I want to convert each of these to moles. So empirical formula is the mole-to-mole ratio of the pieces that make up a molecular formula, right? Or you could think of it as atom-to-atom ratio, but we don't need to get Avogadro's number here involved since the ratio of moles will be the same as the ratio of atoms. So from mass, we can use the molar mass of each element here. 1 mole of carbon is 12.01 grams of carbon. 1 mole of oxygen is 16 grams of oxygen. And 1 mole of hydrogen is 1.01 grams of hydrogen. That will give us moles of each. So 75.69 divided by 12.01 is 6.3. So let's go at least 3 sig figs here. Moles of carbon. For oxygen, 15.51 divided by 16, that's 0.969 moles of oxygen. And then for hydrogen, 8.80 divided by 1.01 is 8.71 moles of hydrogen. Now we want these to be integers or whole numbers, and it's tempting to just round them, but that's not what we want to do. What we want to do is use the same mathematical operation on all 3 pieces of data here. So what we're going to do is divide through by the smaller number, and that's for oxygen. So divide through there, that'll give us 1 mole of oxygen. Now maybe that'll give us integer values for the others. We'll have to see and then go from there. So 6.3 divided by 0.969 gives us 6.5 moles of carbon. And for hydrogen, 8.71 divided by 0.969, typed it in right. That is pretty close to 9. It's 8.988. So for the purposes of a problem like this, that is reasonable for experimental error in measuring those 9 moles of hydrogen. Now, we can't have a half there in our empirical formula. Our empirical formula has to be whole numbers. So that should indicate to you, the actual empirical formula will require a doubling of each of these. So if I double everything, that would be 13 carbons. So 13 carbons, 2 oxygens, and 18 hydrogens would be my empirical formula. Now, conventionally, it's carbon, then hydrogen, then oxygen when you write out a formula for a carbon-containing molecule. Right now, that's not the order they were given in the problem, so I wouldn't expect you to rearrange it that way. But probably should, particularly if you carry on and get some more experience with carbon molecules in organic chemistry as a sophomore. Okay, the next one here, I didn't even write any instructions here on the page. You should know what's going on here. You've got 2 aqueous solutions that are being combined. We want to predict the products, and we want the total ionic and net ionic equations here as well. So let's start by breaking these into their constituent ion pieces for the total ionic equation. Copper nitrate, right, based on charge here, this must be a copper 2. So this is aqueous, that means it's dissolved in water. That means there really is a copper 2 ion floating in that aqueous solution and 2 nitrate ions floating in that aqueous solution. Now, I've got coefficients here from the formulas. Those won't necessarily stay throughout the equation. That's definitely something you need to keep in mind, is you may have to adjust the coefficients here for all of your components. Sodium phosphate, that's also dissolved in the water, so that will break into sodium cations. And phosphate, that's a polyatomic ion, so that's going to stay together in solution. There'll be one of those in their solution here as well. Now, once I have my ions, I can think about the possible reactions here. So copper was soluble with nitrate. Copper doesn't care about the other cation, so it's not going to interact with the sodium. But copper will now have the opportunity of coming in contact with phosphate. There's a solubility rule for phosphates, and it says they're usually insoluble. The exceptions are the metals from the first column of the periodic table, alkali metals, which is lithium, sodium, potassium, rubidium, cesium, right? And the only other exception for phosphates is ammonium, not copper. So copper phosphate, when these ions connect in solution, they are going to link up. They're going to make a solid. That solid is going to precipitate, fall out of solution, and that means we should indicate it as a solid on the product side of the equation, right? It is insoluble. Because of the charges, +2 on copper, -3 on phosphate, we would need 3 coppers and 2 phosphates to make the correct formula for that ionic compound, right? So remember to keep that in mind. That stuff from chapter 2 with the charges and how they are ratioed is important here. Okay, now the other product, we also had nitrate ions and sodium ions in solution. Now sodium nitrate, that is going to be a soluble compound, so those are going to stay aqueous. So in the total ionic equation, we want to keep those as separate and as aqueous. And notice I stopped doing the coefficients because once we got this formula, it was clear we were going to have to adjust some things here. Now, once I have these, I can go back and finish the molecular equation. For me, that's the one I like to balance because I just have more experience treating things in molecular formula form. So I need the correct formula for sodium nitrate. Since it's +1 for sodium, -1 for nitrate, that would just be one of each. But of course, that should still be aqueous there in that top equation. Now, copper phosphate here, if we got the right formula, that really gives us all the information we need because 3 coppers means we'd need a 3 here, and 2 phosphates means we'd need a 2 here. Now that will change everything in the total ionic equation because now we have 6 nitrates and 6 sodiums. So to balance the molecular equation, I'd also need a 6 there. Now if I carry all that through, it would be 3 coppers, 6 nitrates, 6 sodiums, and 2 phosphates. I'd get 1 mole of my product, but 6 nitrate ions and 6 sodium ions left over. Right? We already identified nitrate and sodium as our spectator ions, so to write out our net ionic equation, that would just be the copper cations reacting with the 2 phosphate anions to make our solid copper phosphate. And that would be that, right? A lot of little pieces there that have to be correct to have the right equation. And anything is out of place and you really haven't indicated what's happening in that reaction. So that would be worth maybe some extra practice heading into the final. Okay, let's see if we can finish off this page. So we want to build a seesaw-shaped molecule with fluorines. What other elements would be needed? So a seesaw, let me just use X here for the element in the middle till we figure out what it is. A seesaw would mean we've got fluorines in 4 positions around the central atom, right? And a lone pair in what would be the 5th position of a trigonal bipyramid. So without an atom hanging out over here, that changes the shape, right? And this would be the shape of a seesaw. Now, if we need an atom that looks like that, right, this is how we can figure this out. This atom has 4 bonds, and it has a non-bonding pair of electrons, or a lone pair. That's 10 total electrons, so this has got to be a big enough atom to be able to do that, to go past the octet. But we should always imagine starting with a neutral molecule, so a molecule that would fit into our formal charge equation. And let me use X here again, right? If it's got 4 bonds and it's got 2 non-bonding electrons and we want a 0 formal charge, that means X should be 6. So looking at the periodic table, compound with 6 valence electrons that's big enough to fit in the middle here would be sulfur, selenium, or tellurium. So this could be sulfur, selenium, or tellurium for a neutral molecule. Now, what if it's a plus charge polyatomic ion, right? Well, the fluorines here would all have 0 formal charges, right? We've got the electrons around the outside of the fluorine there too. We shouldn't forget those. But if we want a +1 charge, that really is just going to change this calculation. If we want this to end up equaling +1 instead of 0, right? But the bonds for a seesaw would still be 4 bonds and 2 non-bonding electrons. That would mean we would need a 7 here. 7 minus 4 minus 2. So an atom with 7 valence electrons would just be one column over, right? Chlorine, bromine, iodine would fit that, that possibility. So for a cation, we could have chlorine, bromine, or iodine in the middle there. So that would look something like Cl, F, 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 lone pair. Right? And that means 7 minus 4 minus 2, positive charge there on the chlorine, so an overall positive charge on the whole thing. Okay, we'll come back with another video for the next page of the review.